Okay, good morning, everyone. So, on behalf of the theory department and the other organizers, I would like to welcome you warmly to the CERN Winter School of 2017. So, we all hope that you will have a great time here and you will find you stay productive. This year we have a list of amazing speakers, and we are all looking forward to the lectures. We would like to thank the theory department and the Arnold Sommerfeld Center at LMU for financial support for the school. And let me say a few things about the lectures. As you know, every speaker is going to give 5 talks, and you're highly encouraged to participate during the lectures and ask questions. And every afternoon there will be a discussion session where you will have the opportunity to interact with the speakers of the day and ask further questions, and it's important that you participate in these sessions. The lectures are going to be recorded and uploaded on the website, so if you want, you can go back and watch them again. Now, apart from the scientific aspects of the school, we also have a social program. So today there will be a welcome reception at 6 o'clock, which will take place right in front of the auditorium, and you're all invited for a welcome drink. On Tuesday, we will have the dinner of the school, and it will take place at the restaurant, Restaurant 1. I guess you all know where it is. The dinner will be at 7:30. And if you have any dietary constraints or you want to go for the vegetarian option, please sign up on a piece of paper which you can find on that table. And it is important that you do it during the first break because we want to send the list to the restaurant. On Wednesday, there will be a ski trip if the snow conditions are permitted. And the bus is going to leave at 1:30 in front of the reception, which is building 33, and please try to be on time at 1:30. So there's a talk from 12 until 1. Then you will have a little bit of time to get something to eat, and then you should go to the reception. And the ski trip is going to take place on the French side. So if you want to participate, it is important that you have a Schengen visa. If you have signed up for the trip, but you have decided not to participate, or the other way around, please go to the list which you can find on the table and update it. So cross out your name if you don't want to come, or add your name if you want to participate. Now, if you do not sign up for the ski trip, you have the opportunity to visit one of the experimental groups at CERN, in particular the CLIC group facility, which is the Compact Linear Collider. So there will be a visit on Wednesday at 2 o'clock, and this visit lasts for about 2 hours. And if you want to participate, write down your name. There's an upper limit of 30 people who can attend, so it will be a first come, first serve basis. Now, if you want to pick up your badges, if you have not done it already, you can go there to the reception during the coffee break, and you can pick up your badge, and it is important that you keep it on you at all times. And finally, if you have any questions or if you need help with anything practical, don't hesitate to contact one of the organizers, so me, Boris, Wolfgang, or James, who will be here tomorrow. So I think that's all I want to say. So without any further delay, let's start the morning session with our first speaker, who is Ashoke Sen. Is it on?
Okay, first of all, thank you for the invitation. So these lectures are supposed to be on superstring field theory. Is this visible to everybody? Okay. Okay. So, I will begin by giving a brief motivation for why you want to study superstring field theory, okay, and then I will outline the plan for the rest of the lectures. Okay. Now, it is well known that perturbative string theory, okay, gives an ultraviolet finite description of quantum gravity, at least perturbatively. So, perturbative string theory is ultraviolet finite. Okay. However, it has infrared divergences, okay, just like in ordinary QFT. As in QFT. Okay. And the infrared, I will use the word infrared divergences in a somewhat general sense. Okay. So, for example, in the context of QFT, any divergence that is associated with poles of the propagator I will call infrared. Okay. So, let me give some example of what kind of divergences one encounters in QFT from the poles of the propagator. Okay. So, one example is mass renormalization. Now, let us suppose that we have a 4-point scattering of this kind, okay, in phi cube theory, where there is a self energy. I think it's is this okay? There is some echo, I think. Okay. So, should I switch it off? I can probably be hard without this. Is it? Okay. Okay. So, let us consider a diagram like this in phi cube theory, okay, and suppose the external momentum is p, okay, then by momentum conservation this is also p. And this propagator, okay, will have the form 1 over p square plus m square, okay, where m is the mass of the particle, okay, and this of course is infinite since p is on shell. Okay. So, this is what is called the mass renormalization divergence. Okay. And in quantum field theory, of course, we know how to resolve this. Okay. We know, for example, that whenever there is a divergence of this kind, this means that the external states have masses which are getting renormalized. Okay. And so, we effectively have to shift mass square to renormalized value. Okay. And this means that we sum over all insertions of this kind. Okay, you resum them. Okay, you see this as a shift in the mass square, and once you do that, then you get perfectly finite answer for these quantities. Okay. Another example is diagrams like this. This is for a massless theory. Okay. So, let us imagine that we have again phi cube theory, and we consider a diagram like this. This is massless phi cube. Okay. So, this propagator, okay, is 1 over k square, but this has to be evaluated at k equal to 0, because momentum along this must vanish by momentum conservation, and this is again infinite. Okay. And again in quantum field theory we know what it means. Okay. This existence of tadpoles like this means that the original vacuum that we started with is not a good vacuum. Okay. We have to redefine your vacuum by shifting the field, and then everything becomes fine. Okay. So, for example, here what we will do is that you have a tree level potential which is lambda phi cube. Okay. At one loop you generate a tadpole, which means that the effective potential gets a term of the form some constant times phi, okay. And then you have to extremize this potential. So, this is extremized at phi equal to plus minus square root of c by 3 lambda. Okay. And then what we need to do is to write a new field, introduce a new field which is plus chi, where chi is the shifted field, and expand the action in powers of chi. Okay, and once you calculate the Feynman diagrams from here, you will find that there are no divergences of this kind, okay, because a tree level contribution cancels the one loop contribution by this shift. Now, as I said, superstring theory, okay, certainly has divergences of this kind, okay, and all of these come from degenerate Riemann surfaces. So, superstring theory has these divergences. So, those typically take the following form, okay, that we are in computing string amplitude, we are supposed to integrate over the moduli space of Riemann surfaces. We are summing over all possible Riemann surfaces, and as you integrate over the moduli space of Riemann surfaces, there are certain regions, okay, certain corners of the moduli space where the Riemann surface splits apart into two Riemann surfaces, okay, or sometimes it develops a long handle, okay, and these generate singularities of the infrared kind. Unfortunately, okay, unlike in quantum field theory where there is a systematic procedure for removing these divergences by mass transformation and vacuum shift, okay, in superstring theory, okay, there is no systematic procedure for removing divergences that come from degenerate Riemann surfaces of this kind. Okay. You can, at low orders you can do it by ad hoc procedure, but in high orders it becomes hard to do it that way. Okay. And the main difficulty in doing this is the fact that at any given loop order, okay, in superstring theory there is only one diagram. Okay. For example, the analogues of this diagram and this diagram in string theory, okay, are the same. Okay. There is one single diagram, okay, a genus 1 surface, because this is one loop, okay, a genus 1 surface with 4 vertex operators inserted, okay, whose one region of integration gives rise to divergences of this kind, and another region of integration gives rise to divergences of this kind. Okay. So, you cannot isolate divergences in terms of diagrams, okay, and that in turn means that we cannot sum up a subset of the diagrams of this kind, okay, because there is no analog of what this means in superstring theory, because in superstring theory at 3 loop level, okay, you have only one diagram. Okay. So, this is the key difficulty in resolving or addressing these infrared problems in superstring theory. Are there questions on this? So, the strategy that you are going to follow is to use string field theory or superstring field theory okay, which sometimes I will use a shorthand notation SFT for this to address these problems. Okay. So, given this, let me now describe what superstring field theory means. So, superstring field theory is a regular QFT, okay, with following properties, with some special properties. Okay. So, the first property is not special. Is this visible, or should I try to erase maybe a little more? Oh, okay, maybe next time I'll use the second one. It's okay, I'll use the second one. It's
you have to use the buttons on the side.
Oh, okay, I'll use it. Okay, so the first property, as I said, is not spatial, okay, which is that the amplitudes computed using Feynman diagrams. The second property is that they agree with usual string theory results when the latter are finite. Okay. In other words, when the string theory results do not have divergences of this kind, okay, then what you compute from superstring field theory agrees with what you compute from conventional string theory, because otherwise of course we will not call this superstring field theory. Okay. So, this is a property it must have. got used to it a little bit. Okay. Okay. So third property is that. Oh, thanks. Thank you. Maybe I'll use this one. Okay. So third property is that they formally agree with string theory results even when the latter are divergent. Okay. However, these can be dealt with using QFT methods. Okay. So this is why we want to use superstring field theory, that when the string amplitudes are divergent, okay, superstring field theory tells us how to deal with them. Okay, because this is a conventional QFT where you can carry out the standard analysis. Okay, so here is the brief plan of the lectures. Okay. So first I will give a description of string field theory. Okay. Then I will discuss how to deal with these divergences like mass renormalization. And vacuum shift. Okay. And then finally S matrix. Okay. In particular, I will describe how using this formalism one can prove the unitarity of the S matrix of string theory. Okay. Now for simplicity, okay, we will consider heterotic string theory. Okay. It could be compactified. Okay, so let me write possibly compactified. Okay. But can be generalized to type 2. Okay, it requires more writing, but the technique is the same. Okay. So I will begin by giving a quick overview of the heterotic string worldsheet theory. Okay, so this is basically at the level of Polchinski. Super conformal field theory. Okay, so this I will refer to as SCFT. Okay. So let me begin by listing the fields that this theory has. Okay. So first you have the matter fields. okay, which probably you are familiar with. In flat 10 dimensions, the matter fields involve 10 scalars and 10 fermions. Okay, but in general, you can consider compactified string theory, where the matter fields, part of it will be free scalars and fermions, which describe the non-compact dimensions, and part of it will describe the compact dimensions, okay, described by some superconformal field theory. Okay. So, these are central charge CLCR, okay, as 26 and 15. Okay. Then you have the ghosts or anti-commuting ghosts, okay, which are B, C, B bar, C bar. Okay. So, these are central charge minus 26, minus 26, okay. And then you have commuting ghosts, which one denotes by beta gamma, which have 0 and 11. Okay, the total central charges add up to 0 on both sides. Okay. These commuting ghosts come from gauge fixing the worldsheet local supersymmetry. Okay. So, for carrying out string perturbation theory, we need to bosonize. We can bosonize beta gamma system. Okay, even though the beta and gamma are themselves bosons, okay, we nevertheless bosonize by using a few more fields. Okay. Here xi and eta are fermionic. Okay, which means they anti-commute. Well, maybe I should just write anti-commuting. Okay. Phi is a commuting field. But by the usual rules, e to the plus minus phi are again anti-commuting, okay, and that is how beta becomes commuting. Okay, this is anti-commuting, but e to the minus phi is also anti-commuting. Once we have introduced these fields, one defines two quantum numbers which are very useful. Okay. One is ghost number. Okay. We define the ghost number as 1 for C, C bar, gamma and eta. It is minus 1 for B, B bar, beta and xi, okay, and 0 for the matter. Okay. The other important quantum number is what we call picture number. Okay. Picture number is 0 for C, C bar, B, B bar, beta gamma. Okay. Its q for e to the q phi. It's 1 for xi, minus 1 for eta. Because using these rules you can check that beta and gamma indeed have 0 picture number. Okay. And of course, it is also 0 for matter.
So excuse me, can you explain what the picture number is?
It is a conserved quantum number, okay, just like host number. Okay. But picture number arises only after you are bosonized. You can see that the original fields that we see here, okay, B, C, B bar, C bar, beta, gamma, all of them have 0 picture number. Okay. So, picture number in some sense is an additional quantum number that arises when you have bosonized, okay, because you see that it e to the q phi has non-zero picture number. In a sense, it measures phi charge, you can think of it that way, but xi and eta also carries that charge, so that the picture numbers on beta and gamma are 0. Okay. The importance of this comes from the fact that there is some conservation law. So, you have some anomalous conservation laws. Okay, which tells us that we need ghost number 6 minus 6g and picture number 2g minus 2 on genus G Riemann surface. Okay, otherwise the correlation function vanishes. So, if you are having calculating correlation function of vortex operators on a genus G Riemann surface, you need to have these charges. Are there questions? Okay, we also introduce the notion of GSO parity. So, this is defined to be minus 1 to the f for matter fields. Okay, so f is just a fermion number. Okay, so for in the matter sector, it's simple. The fermionic operators carry GSO parity minus 1. The bosonic operators carry GSO parity 1. Okay. It's 1 for B, C, B bar, C bar. Okay. It's minus 1 for beta, gamma. Okay. And if you want to see what it is for the in the xi q phi system, it's minus 1 to the q for e to the q phi, okay, and then it's 1 for xi and eta. Okay. So, you see that this correlation between fermionic nature and the GSO parity, okay, it's true in the matter sector, but not quite in the for the ghost sector, because xi and eta are definitely fermionic, but they carry GSO parity 1. don't know if it's still visible. Okay, doesn't matter. Okay, so an important operator in the wall slit theory is the BRST operator. So this is the QB BRST operator. So this is defined as integral JB of Z dz plus integral JB bar of Z bar dz bar. Okay, the integration is done around the origin if it's applying if it's being applied on a state. Okay. So JB, let me write down the expressions for JB. This is C times Tm plus C times T beta gamma Okay, so let me explain the various symbols. So this ghosts of course I have already introduced. Okay. So these are the energy momentum tensor in the matter sector. Okay, these are the ones which have central charge 26, 26. This is similarly the energy momentum tensor for the beta gamma system. For beta gamma, okay. And this one is the supercurrent in the matter sector. This is the dimension 3/2 field. Okay, I think rest are all just standard ghost fields, so I don't have to say anything about the rest. Okay. The important point is that we can define a BRST operator with this property. Okay. BRST operator is nilpotent, okay. And the physical states of string theory are defined to be in the cohomology of BRST operator, which means physical states are annihilated by QB and two states which differ by QB on something else are considered as equivalent. Okay, that's the way we define the BRST cohomology for physical states. Okay, are there questions? So another important notion is what is called picture changing operator. Okay, and I'll explain its utility in a few minutes. Okay. This is defined simply as the anti-commutator of QB with xi of z, okay, which I'll denote by chi of z. So this has dimension 0, okay, is primary, has host number 0, and picture number 1. Okay, and it's also BRST invariant because when you take a commutator of this with QB, because QB is nilpotent, the result just vanishes. Then we introduce the notion of small Hilbert space. So, these contains states V0 on 0. Okay, of course, every state in worlds in conformal field theory can be written in this way, some operator at 0 acting on the SL2C invariant vacuum. Okay. But V for small Hilbert space has some spatial properties. Okay, that V is made of products of derivatives, of possibly derivatives of the following quantities. Okay. Matter fields, of course, B bar, C bar, e to the q phi, del phi, eta and del xi. The important point is that xi is missing from this list. Okay, and this is what distinguishes small Hilbert space from the full Hilbert space. Okay. This missing xi, okay, means that the states that we include in the definition of small Hilbert space are not the complete set of states in the full Hilbert space, okay, because that would have included also the xi operator. Okay. So, this is what one means by small Hilbert space. Okay. And throughout these lectures we will be working with states which are always in the small Hilbert space. Okay. In fact, the states will be in the small Hilbert space and will also restrict to GSO even states. Okay. There are some further restrictions that I am going to talk about soon. Okay. So, some definition. HP will be defined as the GSO even subspace of the small Hilbert space that are annihilated by B0 minus and L0 minus. Okay, so let me define what B0 minus and L0 minus are. So, B0 plus minus by definition is B0 plus minus B0 bar, L0 plus minus is L0 plus minus L0 bar. Okay. And these modes of B's and L's are defined by the standard perturbation expansion. For example, B of Z is sum over n Bn Z to the minus L minus 2, etc. Okay, so this defines Bn's and Ln's. Okay. So, this is an additional restriction we put on the states, okay. And as far as the usual string theory is concerned, okay, where you look at physical states, okay, one can show that it's always possible to choose the physical states satisfying all these conditions. Of course, GSO even is a necessary condition for a state being to be physical. Okay. You can show that the physical states can be taken to be in the small Hilbert space, and they can be taken to be annihilated by B0 minus and L0 minus. Okay. The importance of this constraint, okay, in the context of string field theory will be that even when you consider off shell string states, okay, where you of course relax the constraint of it being annihilated by BRST charge, okay, even for off shell string states will implement all of these constraints, that it should be GSO even, it should be in the small Hilbert space, and it should be annihilated by B0 minus and L0 minus.
L0 is Virasoro generator.
Yes, L0 is Virasoro generator. So, T of Z, these are the total Virasoro generator. Okay, and similarly for T bar. Okay, are there questions? Okay. Now, let me say a few more words about picture number, okay, which is perhaps the most mysterious of the quantum numbers of worldsheet conformal field theory. Okay. So, it turns out that there is formal equivalence between physical states in picture number Q and picture number Q plus minus 1 or Q plus minus n for, let me write Q plus n for n in integer. Okay. So, this means that every physical state, okay, has a representative in all picture numbers which differ by 1 or differ by n. Okay. So, in particular the Rebus-Schwarz sector states, which are bosonic states of superstring theory, okay, they have representation for every integer picture number, okay, picture number minus 1, 0, 1, 2 and so on. Okay. The Ramond sector states, which are the fermionic states of the theory, okay, they have representative, okay, in every integer plus half picture number sector. Okay. So, every physical Ramond sector state has a representative in minus half picture, minus 3 half picture, minus 5 half picture, half picture, 3 half picture and so on. Okay. Furthermore, if you calculate the correlation functions of these on Riemann surfaces to compute string amplitudes, okay, one can show that formally, okay, all of these give the same amplitude. Okay. Whether you pick picture number, which particular picture number representation you choose for the particular vertex operator, it does not matter. Okay. This is a formal equivalence, okay, because when I say that it does not matter, what one actually shows is that the results for two different choices of picture numbers differ from each other by integral of a total derivative in the moduli space of Riemann surfaces. Okay. So, to the extent that you can ignore boundary terms, the result is the same. Okay. But often there are subtleties with the boundary terms which make the result not the same. Okay. So, this suggests that at least for in the worldsheet description, okay, where you always work with on shell states, okay, you should restrict to a specific picture number for the Rebus-Schwarz sector and a specific picture number for the Ramond sector. Okay. And there is a canonical choice of this, which is that for Rebus-Schwarz sector we take -1 picture, and for Ramond sector we take -12 picture. So, canonical choice -1 for NS sector and -12 for Ramond sector. Is this clear? Okay, that all NS sector vortex operators will pick the representative from -1 picture, okay, and for all the Ramond sector vortex operators will pick the representative from the -12 picture. Okay. But this also tells us that we have to make use of picture changing operators to compute correlation functions, okay. Because suppose you calculate on a genus G amplitude on genus G surface or genus G amplitude, genus G surface with say M NS sector and N R sector vortex operator, we need to insert (2g minus 2 plus m plus n by 2 PCOs). Okay, so let us see where this counting comes from. You see, if you have m NS sector vortex operator, you have total picture number minus m, because each carry -1 picture number. In Ramond sector vortex operator, we have total picture number minus n by 2. Okay. But I have told you that on a genus G surface, you need total picture number of 2g minus 2 to get a non-zero answer. Okay. So the only way you can get a non-zero answer on a genus G Riemann surface is by inserting in addition these many picture changing operators. Okay, and that's the way you compute the amplitude on genus G. Okay. Now here again the question will be where to insert the picture changing operators. Okay, because on the Riemann surface you can insert an operator anywhere. Okay. And the answer is again that formally it does not matter. Okay. In the sense that if we shift the location of a picture changing operator, what you can show that the result differs by a change in the integrand, which is a total derivative. Okay. So again, as long as you can ignore boundary terms, okay, the result for one particular choice of picture changing operators and another set of choice of picture changing operators will be the same, okay, because the results differ by total derivative. Okay. Now one of the goals of string field theory is to make sure that the results are really unambiguous, that these total derivative terms really do not contribute, okay, and for that we need the formalism of superstring field theory again. Okay, are there questions? Okay. So with this introduction, let me now say a few words about superstring field theory, but tomorrow I will give more details. So what is the general principle of writing down a superstring field theory? Okay. So for this, let us go back and ask in the context of normal quantum mechanics, okay, what do we do when you go from the first quantized to second quantized version. Okay. Because going from the worldsheet description, which is the first quantized description of string theory, to string field theory is like going from the first quantized to second quantized formalism. Okay. Now in conventional quantum theory, when you go from the first quantized version to the second quantized version, okay, what we do is that we take the wave functions or states, okay, and then make them into field operators. This is the way we go from the first to second quantized formalism. Okay. But in doing so, okay, we do not require the wave functions. Okay. The wave functions of course satisfy Schrodinger equation, okay. But the quantum fields that you introduce here, okay, as an off-shell quantum field theory, these do not necessarily obey Schrodinger equation. Okay. These are free field, these are free, okay, they are arbitrary fields. Schrodinger equation for these fields, okay, come as an equation of motion. Okay. It is not put in as a constraint on the fields, they appear once you write down the corresponding quantum field theory, okay, and look at the equations of motion of this quantum field theory, then you get constraints on the fields, and those in some approximation becomes the Schrodinger equation for the wave functions. Okay. So, this is the notion you want to generalize. Okay. So, this means now that the wave functions or states, these in string theory, these are elements of Hilbert space. Okay. So, then the fields of string theory should also be elements of Hilbert space. Okay. The analog of the equation of motion, the Schrodinger equation, okay, in string theory is a requirement of BRST invariance. Yeah, that is the physical state condition. Okay. But just like we do not impose the equations of motion on the fields from the beginning, okay, they come as a result of a variational principle, we will not impose that the elements of the Hilbert space that will then that will denote generic off-shell field will be BRST invariant. Okay, we will not impose the BRST invariant condition. So, this is a general principle of introducing string fields. So, we take the string field psi to be an element Okay, so this I introduced the HP, the notion of HP before, you remember? I think I have erased it now. HP was the subspace of the Hilbert space with picture number P, okay, satisfying this condition that they are analyzed by B0 minus and L0 minus. Okay. So H minus 1, for example, will describe an off-shell Nebel-Schwarz sector string field, okay, which are the off-shell bosonic fields, and these will describe the off-shell Namon sector string field, those are the off-shell formal fields. Now, for technical reason, okay, and this I will try to explain later, technical reason, we will need a second set of string fields which I will denote by psi tilde, okay, and this will be taken to mean element of H minus 1 plus H minus 3 half. Okay. So, it would appear that by including psi tilde, we are doubling the number of fields, because I told you that in H minus 1, okay, for example, every NS sector has a representative. Now, I am taking 2 copies of H minus 1. So, every NS sector physical state will have 2 representatives in this formalism. Similarly, every Ramon sector physical state will have 2 representatives, one in H minus half, one in H minus 3 half. Okay. But we will see that physically we will get only one NS sector state and one Raman sector states. Okay, how it arises we will discuss later. Okay, but right now just keep in mind that we are doubling the number of fields that is otherwise suggested by this formalism. Okay. And this is something that is special for superstrings and heterotic strings. For bosonic strings you do not really need this doubling. Okay, again the reason is technical, I will explain as I go along. Okay. Now normally when you think of fields, okay, we think of these as functions of position. Right? That's where that's the way the fields are thought of. Okay. Now here we have introduced this abstract notation. Okay, you don't see any position dependent object. For example, when I say that the string field is an element of h minus 1 plus h minus half. Okay. So I will now explain how the actual fields that you are familiar with arise from this. Okay, and then maybe I will stop for the day. Okay. So we introduce basis states. Phi r, these are the basis states of h minus 1 plus h minus half, and phi r c of h minus 1 plus h minus 3 half. Okay. So notice that of course these are not all linearly independent because h minus 1 appears twice, right. So there is a representative of h minus 1 in these bases as well as in this basis, but let us just live with this. Okay. And we will impose orthonormality condition which is that phi r c C0 minus phi s is delta r s, which you can say the same as phi s C0 minus phi r c. Okay. C0 minus let me define. So C0 plus minus in our definition will be half C0 plus minus C0 bar. Okay. Again the Cn's are defined by the standard expansion, Cn equal to sum over n Cn z to the power minus n plus 1 etc. Okay. This plus 1 comes because C is a dimension minus 1 field. Okay. So once you have introduced a basis state in h minus 1 plus h minus half and h minus 1 plus h minus 3 half, okay, we can expand a general string field in this basis. Okay. We can expand for example psi as sum over r psi r phi r, okay, and psi tilde as sum over r psi tilde r phi r c. Okay. Now when I say that psi and psi tilde are string fields, okay, what one means precisely, okay, is that these expansion coefficients psi r and psi tilde r, these are the dynamical variables of the theory. Okay. So these objects are the dynamical variables. Okay. These are of course fixed basis states. Okay. And in this sum over r, okay, this sum over r runs over all the basis states. Okay. But this sum over r actually can be decomposed into a sum over discrete labels, okay, an integral over momentum. Okay. These are momentum along non-compact directions. Is this clear? right, because you are summing over all basis states, right, which includes also an integration over momentum, because along non-compact directions the basis states are also labeled by momentum. Okay. So this means that the psi r actually can be thought of as a set of functions of k of momentum, and so for psi tilde r. Okay. And these are the objects that we now interpret as the fields in Fourier space, fields in momentum space. Okay. So these are not directly the fields, but Fourier transforms of the fields. Okay. So it is in this sense that the psi and psi tilde, which are abstract elements of the Hilbert space, okay, actually represent fields, okay, because they really encode an infinite set of functions of momentum, okay, which represent infinite set of fields in the problem. Okay. In particular, in this expansion, okay, there will be one state which represents gravitons. Right? This is the sum over all possible basis states. Right? One particular set of phi r's will be the graviton state that we are familiar with in string theory. Okay. The corresponding expansion coefficient, okay, the psi r, will be called a graviton field or the Fourier transform of the graviton field. Okay. Similarly, there will be a dilaton field, there will be an antisymmetric tensor field, and so on. Okay. So I will not use this expansion explicitly very much. Okay. I will mostly work with psi and psi tilde as an abstract vectors, but anytime you want to see the component form of anything, of the string field theory action or the S matrix element, etc., all you have to do is that you expand these in the complete set of basis states, okay, and regard these as the components of the fields. Is this point clear? Okay. So next time we will begin by writing down an action for the string field, which of course will be a function of this variable psi r and psi tilde r. Okay, and then we will see how to quantize it. Okay. Maybe I just want to mention one thing, that I use this orthonormality condition. Okay. You can easily check that this orthonormality condition is designed so that the total picture number adds up to -2, which is the right number that you need for getting a non-zero inner product in genus 0 surface. Okay, on genus G you need picture number 2G minus 2. So on genus 0 you need picture number -2, and indeed the picture numbers of these and these add up to -2. Okay, I will stop here now.
Thank you very much, Ashok. Questions? Can you turn on your microphone first?
Primary question, why the indices are negative?
Why?
Indices of H.
Well, the point is that you can have states of picture number minus negative or positive, right? Because the picture number we define e to the q phi, for example, has picture number minus q, picture number q, right? So you can easily get the negative picture number states by taking e to the minus phi, e to the minus 2 phi, and so on, right? And as I said, all picture numbers are equivalent, at least formally, right? So you can take a representative of a given state either in picture number -1 or in -2 or in 0 or in 1. Okay. This is just it so happens that these are the canonical choice of picture numbers.
Boris.
So what is canonical exactly about this choice? It's just one particular choice.
Yes, it's one possible choice. I mean, okay. What is special about these choices, h minus 1, h minus half, and h minus 3 half, is that if we look at all possible ghost excitations on these vacua, you can show that the L0 eigenvalues are bounded from below. Okay. Whereas if you take any other picture number, okay, either the gamma or a beta has a mode, a positive mode that doesn't annihilate the vacuum. Okay. For example, in a picture number, in a different picture number, it may so happen that gamma 1 acting on a vacuum is not 0. Okay. In each case, you can take gamma 1 to arbitrary high power because they are commuting objects and get states of arbitrary negative L0. Okay. So only these three picture numbers minus half, minus 1, and minus 3 half, okay, have this property that the energy at the L0 eigenvalue is bounded from below. Okay. So for on cell calculations it doesn't matter. okay, because they are always restricted to physical states. But when you are trying to go off shell, okay, it is really inconvenient if you have states of arbitrary and high negative mass square, right, because the L0 translates to mass square, right, and you do not want states of arbitrary high negative mass square. So, for off shell field theory, string field theory, these seem to be essential.
Okay, if there are no further questions, let's thank Ashoke again.